for one of these representations here to be a probability distribution, we have a couple of requirements. There's some kind of random variable x. So, we have to have a random variable in the probability distribution. That's pretty much always a given. Now this right here, this is very important. Sigma p of x. That means the sum of the probabilities must be equal to 1. The sum of all the probabilities. So if I come back up here to this example here, the sum of all these probabilities, if I add them up, 0.25, 0.5, 0.25, that gives me 1. So the sum of all probabilities of a probability distribution must always add up to 1. Now your book does say that 0.999 or 1.001 are acceptable because they result from some rounding. Okay. Now if it's off by a tenth, then no, that's not acceptable. But if it's off by a 10,000th or a thousandth, then that would be acceptable. Now remember, probabilities cannot be less than 0, and probabilities cannot be greater than 1. All probabilities have to be greater than or equal to 0 and less than or equal to 1. Okay, so if one of the probabilities is negative in the chart, if one of the probabilities is greater than 1 in the chart, it's not a probability distribution. All right, you can draw a histogram for a probability distribution. We call that a probability histogram. Okay, and you can see here, this goes back to the chapter problem, or one of the first examples, where we have no births with girls, 1 of 2 births with girls, or 2 births with girls. Notice that there's no space in between the bars. Alright, and notice that the random variable is exactly in the center of the bar. So that means that it's going to be a histogram, but it's a probability histogram because it's related back to that probability distribution. Alright, let's look at example 2 here. This is a hot topic in the nation. A marijuana survey. In a Pew Research Center poll, subjects were asked if the use of marijuana should be made legal. And the results from that poll have been used to create Table 5.2. Does Table 5.2 represent a probability distribution? So I'm going to go back to 5.2. Off just a little bit. Bear with me just a second. Okay. Here it is right here. Here's the table. Does this represent a probability distribution? Okay. 5.2. So we have yes, no, and don't know. So what's wrong with yes, no, and don't know? Not numerical. It's not like 0, 1, and 2 or something like that. Okay, so the very first requirement for a probability distribution is not met. So no, it does not describe a probability distribution, period. However, if you want to see if it meets the other requirements, add up all the probabilities. Does that give you 1? Yes. Are there any probabilities that are greater than 1 or less than 0? No. So it meets those two, it's just that it doesn't have the random variable there. Okay? Table 5.3. Senior executives were asked, when job applicants discuss salary, all right, their results are in Table 5.3 based on their responses. Does it describe a probability distribution? Let's see. Here's Table 5.3. Number of interviews, 1, 2, 3. Probability, when to discuss salary. I guess if you have 1 interview, 30%. 2 interviews, 26%. 3 interviews, 10%. So as far as the random variable goes, it's there, 1, 2, 3, or some random whole number. Probabilities, if you add all those together, do you get 1? That's 56 plus 0.1, that's 0.66. So no, it doesn't add up to be 1. So since that doesn't add up to be 1, it's not a probability distribution. Now each probability was between 0 and 1, so it only failed that second requirement. All right. So 3 things. If we have a probability distribution or some collection of data and we want to know, is it a probability distribution? First, do we have a random variable? Second, do all of the probabilities add up to 1? And third, are each of the probabilities less than or equal to 1 or greater than or equal to 0? If one of those probabilities is bigger than 1 or less than 0, it's not a probability distribution. Now, if we do have a probability distribution, then we can find the mean of a probability distribution, mean mu, very important formula here, by saying the sum of x times p of x. So we need to make a new column. So, for example, let's go back to this first table real quick. Let's say we wanted to find the mean of this probability distribution. We need to find the mean, according to that formula, said we need the sum of x times p of x. This chart right here, we have the x, we have the p of x. So what we need to do to find the mean is make a new column, x times p of x. Alright? So we'll do that. So 0 times 0.25 is 0. 1 times 0.5 is 0.5. 2 times 0.25 is 0.5. So to find the sum, add all those up. The sum is going to equal 1.0. Well, look right here. I mean, it told you in the table. I just wanted to show you how. So the mean is 1.0. That is the sum of x times p of x. Okay, we'll come back to that in just a second. Look at formula 5.2, the variance. Sigma squared is the variance. All right. The variance for probability distribution, sigma squared, is equal to the sum of x minus mu squared times p of x. All right, so the variance, we use this formula here. This format is pretty easy to understand. But as far as actually working it out, for the variance, I would use this formula. The variance is sigma squared, and I would use the sum of x squared times p of x. So you do that, and then you say minus the mean squared. All right, that will give you the variance. So let's relate this back to that same table. Okay? So variance equals sum of x squared times p of x, and then minus the mean squared. So we have an x times p of x column, but that's not going to help us. We need an x squared times p of x column. Okay? So x squared would be 0 squared, and that times 0.25. What is that going to be? Still 0. 1 squared times 0.5. 1 squared is 1. 1 times 0.5 is 0.5. 2 squared times 0.25. So 2 squared is 4. 4 times 0.25 is 1. Okay? To find the sum of those, add 0, 0.5, and 1 together, and you get 1.5. So if we want to find the variance, that's going to be 1.5 minus the mean, which we've already found, mu, squared. So minus 1.0 squared. Okay, is that right? So what's that going to be? 1.5 minus 1.0. 0.5. So for this, the variance is 0.5. All right. So we got the variance is 0.5 of our distribution, our probability distribution. Now if we want the standard deviation, remember standard deviation is the square root of the variance. So it's going to be the square root of 0.5. All right, so the square root of 0.5 is the same thing as the square root of 1/2, which is the same thing as the square root of 1 over the square root of 2, which is the same thing as the square root of 2 over 2. But using a calculator, if you wanted to get a decimal approximation, all you got to do is say 0.5 and take the square root. So 0.707, you can see in the table here, they have just 0.7. All right, so if we know that we have a probability distribution, you can find the mean of the probability distribution by saying the sum of x times p of x. You can find the variance of the probability distribution. The easiest way is to say the sum of x squared times p of x, and then subtract the mean squared. That gives us the variance. And then if we need the standard deviation, you take the square root of the variance, and that gives you the standard deviation. All right. Round off rule. If the values of x are integers, that's whole numbers, round mu, the mean, sigma, the standard deviation, population standard deviation, and sigma squared, the population variance, to 1 decimal. Okay. The mean of a discrete random variable x is the theoretical mean output for infinitely many trials. We can think of the mean as the expected value, in a sense that it is the average value we would expect to get if the trials could continue indefinitely. So on and on and on forever. The mean is the theoretical outcome we'll have for an infinite number of trials. All right, and your book gives an example, the definition of expected value. The expected value of a discrete random variable x is denoted as E, and it is the mean value of the outcomes. Okay? Just like with some of the data sets that we worked with earlier, where we could use the range rule of thumb to find the maximum and minimum usual values, we can do the same once we have the standard deviation and the mean here, using our formulas for probability distribution. We can find the maximum usual value by taking the mean and adding 2 times the standard deviation. That gives us the maximum usual value. We can find the minimum usual value by taking the mean and subtracting 2 times the standard deviation. So as long as you're between those two values, the maximum and the minimum, then it would be usual. But if you're greater than the maximum or less than the minimum, then it's unusual. It's the same thing from the previous chapters, though. There's nothing different. The only thing is, in the previous, when we worked this out previously, usually we were given the mean and the standard deviation. On problems like this, usually you have to find the mean and standard deviation to find those minimum and maximum values. Okay. And that's called the range rule of thumb. All right, look at this. Unusually high or unusually low number of successes. Not exactly, but at least as extreme. In 4.2, we stated that the number of successes is unusually low or unusually high if that number is far from what we typically expect. We will now refine that description by using a probability value to judge whether a particular number of successes among n trials is unusually high or unusually low. Use the probability of getting x or any other values that are more extreme. Do not use probability of exactly x. For example, suppose you're tossing a coin to determine whether it favors heads or tails, or whether it favors heads. And suppose 1,000 tosses resulted in 501 heads. We can use the methods from 5.3 to make the following probabilities. And you'll figure this out when we get into 5.3. Probability of exactly 502 heads. Actually, I'm thinking that's 4.3, not 5.3. Because we could figure that out, right? You just say, do you remember how to find exactly? Maybe, maybe not. Maybe a little bit too complicated. Because exactly, we're going to have to use a little different method. Also, this is 5-3. Because also, what about 501 or more heads? Do you know how tough that would be? 501 or more heads in 1,000 tosses? That means the probability for 501 plus the probability for 502 plus the probability for 503. And I just keep talking until I said, finally, the probability for 1,000. So you can see that these types of problems would give us some problems trying to work out the methods that we know already, right? There are ways that we will go over in 5-3 binomial probability formula that will help us work out problems like this, these probabilities. All right. Now, usually, I was just scanning over this next problem in the book. It's talking about more about the chapter problem. This number right here that I have highlighted, this probability, 0.05, 5%, that's the value that, if we're talking about probabilities, will decide if something is usual or unusual. In general, if there's a less than or equal to 0.05% chance of something happening, or I'm sorry, 0.05. So that's 5% chance. If it's a less than or equal to 5% chance of something happening, we say it's unusual with probability. So if I say there's a probability that the probability of it raining tomorrow is 3.5%, then that probability would be unusual because it's less than 5%. This problem here, where we're talking about the chapter problem, they want to know, is 879 girls in 945 births an unusually high number of girls? Well, I mean, just using common sense, you can say, yeah, it is. Here it says that when we do get to 5-3, we can find the probability and get something that is, it says 0.000, but it's just because they don't carry it out far enough. Usually a probability like that will be written like this, 0 plus. That just means it's really close to 0. And so something really close to 0 would be, a probability really close to 0 would be less than 0.05. And so since it's less than 0.05, then we'd say that it will be unusual. Okay. Now, expected value. I don't believe we've had a chance to work an expected value problem. And you can use this concept of expected value to figure out how much money the casinos are going to make on a certain game if you know the odds. Now, without using any type of skill, one of the best games to bet on in a casino is roulette, because you can bet red or black, however, or odd or even. However, it's not a 50-50 chance like you would think. Casinos usually will put a 0 and a double 0 on the wheel. And the 0 and the double 0 are not odd or even. They're not red or black. So if it lands on those, people that bet on red or black, people that bet on odd or even, just lose. Doesn't matter what you bet it on. So it's a little bit less than a 50% chance of winning. Over the course of a day, if people are constantly betting on those, the casino is going to make money. Okay? Let's look at this example here on expected value. All right. You have $5 to bet in the Golden Nugget Casino in Las Vegas. You have narrowed your choice to one of two bets. Roulette. Bet on the number 7 in roulette. Or craps. Bet on the pass line in the dice game of craps. Okay? Alright, let's look at both cases. If you bet $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38. It means there's 37 other choices out of the 38 total choices. And the probability of making a net gain of $175 is 1 out of 38. It says here the prize is 180, but you've already bet that 5, so you don't count that as part of your winnings. Find your expected value if you bet $5 on the number 7 in roulette. Okay? So to find the expected value, it's best to think about the expected value whether we lose or whether we win. Then you think about the random variable is either you're going to lose $5 or you're going to gain $175. Okay? Expected value is the sum of x times p of x. Expected value is the sum of x times p of x. So we need to find the value if we win. So it's going to be the random variable -5 times the probability of that happening, 37 over 38, which is -4.868421. Okay? And then the random variable, if you win, you get $175. The probability is 1 out of 38. Multiply those together. That's $4.605263. If you take the sum of those two, that gives you the expected value. So -26 cents. Okay? That means that over the course of time, you would lose 26 cents per $5 that's betted on number 7. If you could win $175 if you won. Okay, so that's one bet. See, right here above it says you can expect to lose an average of 26 cents. Now, the dice game. So that was one game. That was the roulette. Let's look at dice. If you bet $5 on the pass line in the dice game of craps, the probability of losing $5 is 251 out of 495. And the probability of making a net gain of $5 is 244 out of 495. If you bet $5 on the pass line and win, you're given $10 that includes your bet. Okay, so you actually only win 5. Find the expected value if you bet $5 on the pass line. We're going to have this probability here. So, again, make a little table. So, if we lose $5, that's -$5. The probability is 251 out of 495. The probability of winning $5 is 244 out of 495. So, the expected value, on average, you're going to lose, if you say x times p of x, x times p of x, add them together and round, you're going to lose an average of 7 cents. Alright, so what does that mean? That means that in craps, over time you're going to lose less money. Neither one of them are you going to, if you made those bets that they suggested, are you going to win over time. The pass line in craps, I guess you could think of it would be more bang for your buck. If you had a lot of money and you wanted to go to the casino and play all night long, go bet on the pass line. Okay? Because over time, yeah, you're going to lose unless you're lucky that night. But over time, you're going to lose slower. Now, that doesn't mean that you're not going to lose your money. You're probably still going to lose your money. But That'll be a way to burn some time, I guess, if you know you got to be at the casino. All right. So let's look at this chart here. First, I want to know, does this chart represent a probability distribution? Okay. So let's see. This is male color blindness. For this to be a probability distribution, I need to have a random variable. Looks like that's happening, right? I need to also have no probabilities greater than 1 or less than 0. Looks like it's happening. The last requirement is I need to know, do all of the probabilities add up to 1 or something that is very, very, very close to 1. So let me see. Alright, so it says I have 1.001. So your book said that was acceptable because that's super close. This last one here, 0 plus, we don't add that there, so it must be a really, really, really small probability. Alright, now let's take this set of data and I want you to find the mean, the variance, and the standard deviation. Alright, so you need to make a column that's x times p of x. Make a column that's x squared times p of x. Once you do that, sum up the x times p of x, and that will give you mu, or the mean. I get 0.403. So if I round that to 1 decimal place, that means my mean is 0.4. Alright, to find the variance, you have to find the sum of x squared times p of x, and then subtract the mean squared. Alright, so add these numbers together here. Let me do that real quick. Alright, so I got 0.539. Does that look right? And what do I do with that? I say that value minus the mean squared. So the variance equals 0.539. Don't round anything yet. 0.539 minus the mean squared. Don't forget to square that mean. Alright, so when you do that, you get 0.379. Okay. If you want the standard deviation, you just need to take the square root of the variance. Now, I guess technically this would be, the variance would be 0.4, but don't use a rounded variable when you find the variance. I'm sorry, when you find the standard deviation. Don't round, use the exact number. So take the square root of that, and I got 0.6156, and the decimal keeps going on, which is approximately 0.6. Okay, so that is mean, variance, and standard deviation of a probability distribution.